Alrighty folks, so as we have done in our previous sections, we're going to start with talking about ideal gases as a model, and we can use that to build up discussing equilibrium of more complex systems. So back to our very simple equilibrium expression, A is in equilibrium with B. We established that the free energy change of that reaction can be simply as the chemical potential of the products minus the chemical potential of the reactants. And if you recall from our previous sections, we came up with an expression for the chemical potential of an ideal gas as the following. So chemical potential equals the chemical potential of some reference value plus RT times natural log, and this would be, so sorry, I'll put a subscript J to note that we're talking about generic species J. And that would be the standard potential of J. And now that would be then given by the pressure of J over some reference value, which recall we take that reference value to be 1 bar. So now filling in all of that stuff here, we can say the following. So the Gibbs free energy of reaction is going to be the chemical potential of B, which I'll just write directly as the following. Chemical potential standard plus RT natural log of PB over P standard. Okay, and then now that's all minus the chemical potential expression of A. So we'll just fill that in there, PA over P standard. And then now we can do some algebra here. So let's go for it. So we have delta G of reaction. I'm going to combine the standard chemical potentials, mu B minus mu A. And then now I'm also going to do some algebra with our natural logs, noting that when we have natural logs being subtracted, we can take that as a division. And additionally, we can see the P standard will cancel out. So just writing all of that down, that's going to be RT times the natural log of PB divided by PA. Okay, well, recall from your standard, sorry about that. Let's keep going. One more algebraic step to do. So delta G reaction. And then now this quantity mu B minus mu A, I'm just going to write that as delta G standard. Okay, so now we have like these two things that are going on here. We have our standard free energy of reaction, and then we have the delta G of the reaction. So standard means just that, right? All right, standard. Whereas this one is really describing the whole process, okay? So I'll write whole process. And what that whole process is in reference to is not only the free energy of the reaction, but the free energy of just mixing those two things in the first place, right? If you recall, when we talked about ideal gas equilibrium, we noted that when you mix two gases, and that's mole fraction, there is a minimized Gibbs free energy based on a 50-50 mixture, right? So looking at how that would manifest in this whole process, let's rewrite that equation. I'll just say delta G Rxn equals delta G Rxn standard plus RT natural log of PB over PA. And then, of course, remembering here that we could write the equilibrium constant as PB divided by PA if those are equilibrium amounts. Or recall we use this thing called the reaction quotient corresponding to the initial amounts, right? So as it turns out then in this expression, when this delta G reaction, this one right here for the whole process, is not 0, we are not at equilibrium. Thus, we would write that as delta G Rxn equals delta G Rxn standard plus RT natural log of Q. So I'm replacing PB over PA with Q. And when we have achieved equilibrium, we know that this delta G will be 0. So we still have a standard free energy of reaction, but now we can replace Q with K. And thus we have another way of thinking about how to compute our delta G of reaction by the following, right? So I'll do some algebra on this thing. And we'll say here that that's negative delta G Rxn equals RT ln K. I'm going to divide both sides by RT and then take the E of both sides. And what I get is the following: K equals E to the negative delta G. Let me make sure that I get all those qualifiers in there. Rxn G standard all divided by RT. So this is a way that we can also compute the equilibrium constant with only knowledge of the free energy of the reaction. And now to see what I mean about this thing referring to the whole process, here is a figure demonstrating just that. So if we think about delta G, right, as being something related to, G final minus G initial, that shows us this simple line here without mixing, right? So that would be my initial free energy, and that would be my final free energy. And all we get from that is just this simple line, right? Because it's a state function. Well, what we also have to remember is this whole RT natural log thing, that describes the mixing quantity right there. And for this simple mixture of A and B, right, that always has that 50-50 mixture. So now when we add the delta G of mixing, so we add this line to this line, we get the delta G for the whole process that I'm going to outline in red right here. And you can see then by adding those two lines together, we get where that delta G of the whole process is equal to 0, and thus where we find our equilibrium, okay? And so let's see, I think that's all that I wanted to say about this. So we're going to now use this expression that we've obtained for ideal gases and apply it to more complicated systems. I'll see you then.